Hello everyone, thank you for joining our project to presentation, retail sales analytics and real-time demand forecasting. Our project focus on building a robust data processing pipeline for analyzing retail sales data, predicting damage, extracting customer sentiment insights, and monitoring transaction in real time. We utilize PySpark for scalable processing, Spark SQL for data querying, Spark Streaming for real-time analytics, and MLlib for machine learning tasks. So now we'll go through the task one implementation where we have focused on data loading, cleaning, and exploration. The objective of this task one was to prepare our data set for analyzing by loading the data into PySpark, cleaning it, and exploring the structure and the quality of the data. So in this code, if you see, first we have done is data loading. We work with two data sets, a sales data and a review data set. The two were ingested as PySpark data frames using spark.read.csv with a header line info and schema automatically detected. And the next step that we did is data exploration. We printed the schema and performed an initial quality check to identify missing values, duplicates, and data inconsistency. Using a loop, we calculated the count of missing values for each column. This step provides insight into the area requiring cleaning. For example, we found a static state specific issue, example missing date value in X row or duplicate record in Y data set. And the next step that we did is data cleaning. To address this issue, we used PySpark drop duplicate to remove duplicate across both data sets. Missing values were handled using na.drop or filling using fill now method, depending on the column relevance. For columns with dates, we converted them into consistent formats in the format of like year, month, and date using to underscore date method. And here is a snippet of the code for cleaning. This ensures that data was uniform, clean, and ready for further analysis. And the output for our task one, if you see here, is like for review data and for the sales data, this is the cleaned output. So we have ingested the input to the program for the task one, and this is the output that we received. And now let's go to task two implementation. So in task two implementation, which focus on sales data aggregation and feature engineering. Our key objective in this task were calculating total sales per month, per product per month, determining the average revenue per customer segment, identifying seasonal pattern for top selling products, creating derived feature for deeper insights such as customer lifetime value, and product popularity score. We achieve these goals using PySpark data frame operation and a Spark SQL. And let me explain like each step in detail. So the step one that we did here is we begin by converting the invoice date column into a proper date format using PySpark toDate function. This was crucial for aggregating data by months and extracting seasonal pattern. Here is an example. The invoice date column was passed into consistent format, month, date, and year format. This allows us to group transactions by month and perform time-based aggregations. And in the step two that we did is like sales aggregation. Uh, the total sales per product per month. We did this using PySpark group by function and aggregate function. We group both the data by stock code and month to compute total sales for each product. The results were saved as a CSV file for further analysis. The average revenue per customer. To calculate average revenue per customer, we group data by customer ID and use the average function on the unit price column. This metric highlights customer spending pattern. And the next one and last one is like seasonal. pattern for top selling products. By grouping data by stock code, month, and then calculating the total quantity sold, we identified a seasonal trend. For instance, certain products showed a peak during holiday month or specific season. In the step three, we now focus on feature engineering. In addition to the aggregations, we derived a new feature to enhance our analysis, customer lifetime value. Using the total quantity purchased per customer lifetime value, we provided a clear instructor on customer importance. Product popularity score. We counted the number of transactions for each product to rank them based on popularity. Seasonal trends. For each product, we analyzed monthly sales to uncover periodic trends. This was particularly used for forecasting demand and planning inventory. And for the after executing, this is the output that we received. Let me just show you. So this is the output for the task two. So here, if you see, the outputs consist of like total sales, seasonal patterns, derived features. So we have generated CSV files summarizing sales for each product by month, and visualized trends using tools like Matplotlib, showing clear spikes for certain products during peak months, and metrics like customer lifetime values and product popularity score provided actionable insights for decision making. So these are the values. If you could see, this is for average revenue per customer and customer lifetime values. This is the value. And for the product popularity score, this is the output. For the seasonal trends, this is output. And for top selling products, and for total sale per product per month. So in this way, like we have successfully implemented the task two. And for the takeaways, for the task two is like aggregating. To summarize, task two involves aggregating sales data for meaningful insights, engineering features that enhance predictive analytics, identifying patterns to inform damage, forecasting, and inventory management. With these results, we've set the foundation for real time demand forecasting and subsequent tasks. And thank you. I'll will now proceed with task three. So now let's move to the task three implementation, where we developed a demand forecasting model using Spark MLA. The goal of this task was to predict demand for popular products using historical sales data. To achieve this, we applied a machine learning pipeline with the following steps: feature assembly, data scaling, and model training and evaluation. So we'll go through each and every step one by one. So for the first step, I'll talk about the data preparation. We start by pre-processing the sales data. The invoice date column was converted into consistent data time format using a to underscore date method function. We dropped rows with missing values to ensure data quality. Using PySpark function, we extracted year and month from the invoice date column and grouped the data by these features along with stock code. The result was an aggregated data set showing the total quantity sold for each product in each month. And the second step, I'll talk about like feature engineering. To prepare the data for modeling, we used a vector assembler to combine year and month into a single feature vector. The feature vector was scaled using standard scaler to normalize the input features for the regression model. These steps ensures that the model was trained on appropriately scaled and engineered features. And the third step, we'll talk about once again. Yes, here it is. And the third step, we'll talk about modern building and training. For the forecast model, we choose linear regression from Spark MLA, which works well with structured data like ours. A pipeline was created to streamline the process, incorporating feature assembly, scaling, and model training. To fine tune the model, we used a cross validator with a param grade builder to test different combinations of hyperparameters, including regularization parameters, reg param to control overfitting, elastic net parameters, elastic net param for balancing L1 and L2 regularization. This approach ensures an optimal configuration for our model. And the next step we'll talk about like modern evaluation. After training, we evaluated the model performance using root mean square error, which measures the standard deviation of residual mean absolute error, which calculates the absolute magnitude of errors. So this metric indicates that the model effectively captures the data underlying patterns. So the last step will look into the output for the execution of this task 3. So here is the output for the task 3. Here if you see the output for the task 3, root mean square error. So the root mean square error that we received on the test data was this is the value. And for mean absolute error, so this is the output that we received for the test data, 184 point some decimal values. So regarding this output, like the trained model was used to forecast demand for popular products. The predictions were compared against actual sales, and the results were visualized. And the takeaways from this task 3, the power of the Spark MLF for scalable machine learning, the importance of feature engineering and empowering model performance, the accuracy of the model in forecasting demand, as shown by its low error metric. This task laid the groundwork for integrating predictive analytics into real-time decision-making processing. And let's move to task 4 implementation. So now let's discuss task 4, where we focus on analyzing customer segment sentiment using review data. This task was designed to provide insights into the customer opinion, helping identify positive and negative trends for different products. So there are like few steps that I'll divide this task for implementation into like a few steps. Let's go through each step, explaining them in detail. So the first step, I'll talk about the objective. So our key objectives were pre-process the review text to extract meaningful features, build a classification model to determine the sentiment polarity, positive or negative, calculate aggregate sentiment score for each product. And the next step we'll look into is text processing. We begin with text processing using Spark, PySpark, and PLP library. Tokenization, breaking sentences into individual words, stop word removal, eliminating word, common words like the and is. To focus on significant terms. Ngram, generating bigram to capture contextual word relationship. So to better explain the scenario, the sentence, let's say like there is a sentence called "This product is amazing," was tokenized, filtered, and transformed into bigram like "product amazing." So simple conversion. So the next step we'll see is feature engineering. After pre-processing, we combined filtered words and bigram into a unified feature set, applied hashing TF to convert text into a numeric vector, followed by IDF to emphasize unique and significant terms. This transformed the text data into a format suitable for machine learning. So for sentiment classification, we trained the logistic regression model using PySpark MLlib to classify sentiment, and labels were assigned based on sentence context, positive or negative. And the data set was split into training and testing was set into 70 to 30 ratio. The model's parameters were tuned to optimize performance, and it predicted sentiment for new reviews. And the next step that we look into is yeah, here it is. Model evaluation. So the model was evaluated using the area under ROC curve metric, which measures the classification accuracy. AUC score is 85%, indicating strong predictive performance. And aggregate sentiment analysis using the prediction, we calculated average sentiment score for each product with high score reflected more positive customer feedback. These results were saved as a CSV file for further analysis. So for the results for this task force is so this is the output for product sentiment analysis for task force. This is output, and the area under ROC is like 1.0. So this is output for the task force. Now we'll look into the takeaways from this task force. To conclude, our test processing and feature engineering was critical for sentiment analysis. The trained model provided reliable sentiment prediction, aggregate sentiment score, offer actionable insights into a customer satisfaction. And this is it for the task force. We'll go to task 5 implementation. So this is the task 5 implementation. Here we have like two programs written for this task 5. One is for consumer and one is for producer. So this task 5, which involves setting up a real-time transaction monitoring. This task aim to process streaming transaction data, dynamically calculating running total for product sales and detect anomalies in real time. So the step one objective here is simulating real-time transaction streams with fields like product ID, quantity, and I think yes, here it is, right? One second. Yeah. Calculating running total sales on each product, detecting anomalies such as unusual high quantity or sales. Data simulation, we used a Python script with the socket library to simulate transaction streamer stream. This server continuously generate random transaction records, including product ID, quantity, which includes product ID, a unique identifier for the product, and quantity simulated realistic purchase pattern, and so and the next field is quantity simulated realistic purchasing pattern, price randomized within a reasonable range, timestamp recorded with when the transaction occurred. The simulated data was sent over a socket connection to our Spark streaming application. The next step we'll look into is real-time processing with Spark streaming. So one Spark streaming pipeline process this incoming data as followed. Data passing. The incoming transaction data was passed and keyed by product ID. Running total, we used the update state by key function to maintain the stateful computation of total quantity sold per product, total revenue generated by product, anomaly detection, transaction exceeding threshold. Example, quantity, if quantity is greater than 10 and sales is greater than $5,000 were flagged as anomalies. So let's say an example for a product with unusual high sales or large quantity, the system immediately flagged it for review. And Let's now look into the output for the task 5. So these are the outputs that were generated. Once again, this one, sorry. Yes, so here it is. So the output that you see here is like running total continuously updated and written to the output file. Anomaly flagged anomaly were saved as a separate output for monitoring. Additionally, these outputs were visualized on the dashboard, allowing us to monitor real-time sales trends and flagged anomalies dynamically. So the key takeaways from this task 5 is data simulation. The socket server streamed dynamic transaction data with varying interval and realistic pattern. Spark streaming pipeline. The update state by key function was used to maintain running total. Anomalies were detected based on predefined threshold and saved for further analysis. This pipeline demonstrates how we can integrate Spark streaming with simulated real-time data for actionable insights. And the power of Spark streaming for processing real-time data efficiency, the ability to maintain running total and flag anomalies dynamically, practical application for retail business such as identifying sales trends and monitoring suspicious transactions. These are the takeaways we can take from the task 5. And let's now talk about our project contribution. Let me close all these things once again. So our team size is like 5 people. Sriyukta worked on task 2, handling sales aggregation, feature engineering to extract meaningful insights. And Nitin, he focused on task 3, developing the damage forecasting model and tuning hyperparameters for optimal performance. And Lakshman, he led 4 tasks, conducting sentiment analysis and evaluating the sentiment classification model. And myself, I managed dashboard development, ensuring seamless visualization of results and contributed to project documentation. And Abhinav and myself took ownership for task 1 and task 1, covering data cleaning, exploration, and real-time transaction monitoring. And as a team, we collaborated daily, integrating our tasks seamlessly to meet the project objectives with regular meetings, brainstorming sessions, and consistent communication ensured the success of our project. So, to conclude our project two, our project retail sales analytics and real-time demand forecasting provides valuable insights in for the retail domain. We cleaned and aggregated data, laying a strong foundation for analysis, forecasted demand with reasonable accuracy to assist inventory planning, analyzed customer sentiment, offering actionable feedback for product improvement, monitored real-time transaction to detect anomaly and ensure operational efficiency. So this project demonstrates the power of data-driven decision making in the retail sector. Thank you for reviewing our submission. We really hope that you enjoy our presentation.